In this final video for the day, what I like to do is walk you through some of the equations that you'll have to use. I used to actually write these out on the board and talk about them, and I found that just actually having them on just a simple PDF is equally as efficient. But I would like to spend just a few minutes walking you through making sure you understand what the different parameters are that go into these different equations. So we're going to zoom in and we're going to start with the bending moment at yielding and the plastic bending moment. These two equations right here, bending moment and plastic moment, they have to do with determining what the allowable moment is when the beam will yield and when it reaches that plastic hinge state or the plastic moment condition. And the equations are both similar. They both have in there a yield stress value, and they both have in there a section modulus. It doesn't want to write section modulus value. For the upper one, it is the section modulus that we're used to seeing, the capital S, where that was the moment of inertia divided by the distance from the neutral axis to the extreme fiber. In other words, S equals I over C, if you remember that. The lower one is a similar value, except we just pull it from a table, and it tells us what the section modulus will behave like at that yield point. The first homework problem is as simple as grabbing those values, plugging them in, and then comparing the ratio. And so we won't spend much more time with that, but you'll know how to calculate both of those so we can determine what the moment capacity is for both yielding as well as plastic section. So, all right, let's erase that. Next thing I want to do is recognize here that there's a couple different equations that show up. Generally speaking, this next equation is the LRFD equation for bending. And I've put it in the same form as what we saw in the PowerPoint. I think it's actually backwards from what we had in the PowerPoint. But on this side over here, we've got the failure mechanism that we reduce. On this side over here, we have the moment that's created by the external loads. We increase our loads and bring that up, and we just want to make sure that the left side still remains greater than the right side. And so you'll see that in what we end up doing. This is the actual equation. It's the design form of the equation, where we're now basically what we've done is we've come up here and we've substituted in our nominal failure, the ultimate bending capacity. So on the left side, you've got your, if you were to cross multiply here, you'd have your yield stress times your plastic section modulus, which in essence is the M over P equation. The phi for bending is the 0.9 that reduces it. So we're just really looking at the left side of that equation right there. The right side of the equation, the 12 is simply a conversion factor that takes, usually our answer is either in foot-pounds or kip feet. And this converts it and makes sure that we're dealing with inches, kip inches, because that's typically what the moment of inertia value, or sorry, the section modulus value ends up being. The shear equations are fairly easy to manipulate once you get which case it is, but you'll notice that for each one of these cases, there's a different set of parameters that holds true. What we end up doing is needing to compare the height of our beam. So this ends up being the height of our beam to the thickness of the web. So essentially what we're doing is we're comparing the slenderness ratio for the interior of the beam. And you'll notice that that part of the equation holds true in all three cases. There's two empirical formulas that help us determine whether it's case 1, 2, or 3. And all we do is take the square root of the yield stress, 50 KSI or 36 KSI. I believe that you plug those in KSI, so it'll be this. You'll see how we do that in the example. Divide it by 418 or 523, and if that slenderness ratio for the web part of the beam is less than the 418 over square root of Fy, then it's case 1, and we would use this equation. Otherwise, if it's in between that and 523 over square root of Fy, we would use this equation, and if it's greater, we would use this equation. One thing I want you to note is that your textbook only introduces this equation right here. They only introduce the case 1. I've thrown the other two in there just in case you ever run across a situation where you need to do additional calculations because it doesn't fit the parameters. But for most of the time, you're going to be a case 1 scenario. One other thing that I would like to note here is that the area of the web is this center portion that we talked about where we approximate the full depth of the beam multiplied by the thickness of the web, and that gives us the area of the web that we want to deal with in the calculation. This is a design assumption that lets us simplify what we're working with. Beam compactness is a special set of calculations that we do just to simply check and see if the beam is capable of failing in a plastic hinge. The thickness of the web, the thickness of the flange, the height of the web, the width of the flange, these proportions all have to be kept relative to each other so that we can make the most efficient beam possible. And we want it to be able to fail in the plastic hinge situation. Now, I slightly missaid that. We don't want our beams to fail, but we want it to have the capability, if it does fail, to use that plastic hinge scenario, because then we've maximized the dimensions in such a way that we're getting the most out of the amount of material that we're using. This is just a simple calculation that we check. This is essentially the same calculation we just did previously with the shear, where we're checking the slenderness ratio of the interior of the beam. Whoops. So it's this height is this one, sorry. And this one is the thickness of the web. Checking the slenderness ratio of that. And the other one is simply the width of the flange, B sub f, and this one is the thickness of the flange, but you've got one on top and you've got one on bottom, so there's two of them, and you're essentially checking those ratios. And as long as you stay less than these two empirical parameters, whether you're using 36 KSI still or 50 KSI still, then your beam should come out okay. The final calculation that we check is another empirical equation that we check the minimum umbrace length. This is for lateral buckling of our beams. And it's simply 300 times the radius of gyration for the weak axis divided by the square root of the yield stress, or the yield strength. And I'm not going to go through this one in any more detail than that. It's simply grab the radius of gyration, plug in your yield stress. But what it'll do is it'll give you an answer, say 49 inches or 50 inches is the number that you've got to brace. And what you'll do is you'll pick a nice happy number that's less than that, say 48 inches, and then we would brace the beam every 4 feet to ensure that we don't have any lateral buckling of the beam take place. So there's the equation sheet. By itself doesn't make a whole lot of sense. If this video is a little bit confusing, start the examples, and then if you need to come back and reference these equations. You've got them here to use. For the most part, these equations are simply plug and play, grab the right values, put them in the equation, get an answer, follow the procedure, and that's what these equations are here for. However, I want to give you a little bit of a heads up on what is happening in these equations so that you could understand a little better as you use them.